This is another video in my series on calculus concepts. In this video, we're going to learn how to compute the value of the derivative of a function at a particular point, and we're going to look at functions that are presented in several different ways. We'll look at a numerical function, which is just another way of saying a table of values. We'll look at a graphical function, and then we'll also look at an algebraic function, in other words, a formula. Let's first remind ourselves what a derivative actually represents. Remember that what we're looking for is the instantaneous rate of change of the function. So given a function and its x value, f prime of a is going to be the limit as x goes to a of f of x minus f of a divided by x minus a. And remember that this is really a change in y over a change in x. This top of this fraction is a difference in y values, f of x minus f of a, and the bottom of the fraction is a difference in x values, x minus a. As x gets closer and closer and closer to a, this slope is going to be getting closer and closer to the instantaneous rate that we're looking for. And we'll see how that plays out in the various different types of functions that we're going to look at. So in this case, we have a numerical example. So this table of values is looking at altitude versus average annual temperature at that altitude. So at 0 feet above sea level, the average temperature is 59 degrees. At 5,000 feet above sea level, the average temperature is 41.2 degrees, and so on. And so the question is asking us, so this is the question right here. At what rate is the average temperature changing at 12,000 feet above sea level? So remember that we're looking for a rate of change. So we're looking for a slope. And in order to find a slope, we need to have 2 points. So one of our 2 points is going to be the point at which they're asking about. They're asking about 12,000 feet above sea level, so we're going to look at 12,000 feet above sea level. That's this entry in the table. The second point that we're going to pick is going to be another point that's nearby. And we want the second point to be as close as possible to the first point. So we have 2 choices. So if we look in our table, we've got another point here, 7,000 feet above sea level, and another point here, 14,000 feet above sea level. So the thing that we're asking ourselves, and we're looking at the x values, to determine closeness, we're looking at x values. So we're asking ourselves which is closer to 12,000. 7,000 or 14,000. And hopefully we can see that 14,000 is closer to 12,000. It's only 2,000 away, whereas 7,000 is 5,000 away, so that's further away. So we're going to use the 14,000 point as our second point. So let's see how this works out. So now our 2 points are 12,000 feet above sea level and 14,000 feet above sea level. So our slope, our rate of change, is going to be approximately equal to, remember when we actually use 2 points, all we're getting is an approximation. The only way that we would figure out the exact value of the rate of change is if we could actually take the limit, and we'll talk about that towards the end here. So the rate of change is going to be our change in y over a change in x. So that's going to be the 2 y values, which are 9.1 and 16.2, change in y on the top, and the 2 x values on the bottom, 14,000 minus 12,000 on the bottom. So on the top, that gives us negative 7.1. On the bottom, that gives us 2,000. When we divide that out, we get negative 0.00355. And this rate has units as well. On the top of our fraction, these were degrees Fahrenheit, and on the bottom of our fraction, these were feet. And so degrees Fahrenheit divided by feet, degrees Fahrenheit per foot, that's the units of our slope here. So let's go back to what I said before about why this is an approximation rather than an exact value. Remember that the exact value of the derivative is the limit as the 2 points get closer and closer and closer together. But we are limited by this table of values. We can't pick any other point that's closer to 12,000 than the 14,000 point, because that was the only other piece of information that we got. All the information we have is in this table. So there is no other point that's closer to 12,000 than the one that we chose. So if we really wanted to get a more accurate sense of the derivative here, we would have to collect more data. Okay, let's move on to another example. So in this case, we have a graph. So this graph shows us the profit of a company as a function of how many items they sell. So the items sold, that's my x value. The profit in thousands of dollars, that's my y value. And the question is, at what rate is the profit changing when 150 items are sold? Now, again, this is going to have to be an approximation, but for a couple different reasons now. So our first point is when x is 150, and now we're going to have to estimate as best we can what is the y value when x is 150. And so we come over here on our y-axis, and it looks like it's about 1 tick above 30. So how much is each tick? Well, we got to figure that out too. If you notice, between 20 and 30, there's 20. I've got 1, 2, 3, 4, and then 5 ticks gets me to 30. So 20 to 30 is a distance of 10, and then 5 ticks, that means that each tick is 2. So if my point here is 1 tick above 30, that means my y value is 32. So this point here, the coordinates are 150, that's my x value, and then 32 is my y value. Okay, so what do I pick for my second point? Well, I want to pick a second point that's as close as possible to my first point. But I don't have a limitation like I did in the previous example, where all I have is a table of values and I'm restricted to only being able to pick one of the points in the table. Now I can pick whatever I want. But if I try to pick a point that's really close to 150, I'm going to have a hard time distinguishing that y value from the y value that I already picked. So I want to pick it a little bit further away so that I can actually tell the two y values apart. Right here, we're going to have to approximate because we don't have exact y values. All we have is a picture, and we're going to have to approximate it as best we can. So let's get a clean picture here. So our first point is here, 150, 32. We already figured that out. Let's pick a second point. Let's do 200. Again, this is not the only way to do this, but I'm going to pick 200 just because it's far enough away so that I have a distinguishable y value. So when I do 200, I carry this across, trying to keep my line as straight as I can, and it looks like it's right around that third tick above 30. So that would mean, remember, each tick is 2, so there's 30, there's 32, there's 34, so it looks like that would be 36. So 200, 36. Is it exactly 36? Probably not, right? But I'm doing the best I can with the information that I have. So my slope would be approximately change in y over change in x. So that's going to be 36 minus 32, and then divide by the corresponding x values. So 200 minus 150. That gives me 4 on the top and 50 on the bottom. And that's going to be 0.08. And again, I have units here, right? So the 36 and the 32, those were y values. So that's going to be thousands. Oh my gosh. Let me fix that. So thousands of dollars. That's what's on the top. And then on the bottom, those were items sold. So my units here are going to be 0.08 thousand dollars per item. And if I want to clean that up a little bit, 0.08 thousands, so that's 0.08 times 1,000, that's actually 80. So another way I could write this answer is $80 per item. And again, that's an approximation to my derivative. That's the actual slope between these 2 points, but it's an approximation to the derivative that I'm looking for because I didn't move the 2 points closer and closer and closer together. Again, if I was trying to get 2 points that are closer, I probably could have gotten a second point that was a little closer than 200, but again, the downside of that is that I'm making more of a guess as to what the actual y value is. So it's good to give yourself a little bit of space on these graphical examples so that your 2 points aren't exactly right on top of each other. Okay, finally we have an algebraic example. So this time we're given that f of x equals x squared plus 5x, and we're asked to compute f prime of 3. So this time we're actually going to be able to compute f prime of 3 exactly. In the previous couple of examples, we've only had to live with approximations, but here we're actually going to be able to compute the limit because we have a formula. So remember, our definition is that f prime of 3 is the limit as x goes to 3 of f of x minus f of 3 divided by x minus 3. So we know what f of x is. That's the formula that we're given, so that's x squared plus 5x. What's f of 3? Well, we can go off on the side and figure that out. F of 3 is 3 squared plus 5 times 3. That's going to be 9 plus 15, which works out to be 24. So that goes there. And then we've got x minus 3 on the bottom. So now we have an algebraic limit that we're trying to figure out. It's a polynomial divided by a polynomial. And what we've learned is that we can try to figure those out by factoring. So if I can factor the top of that fraction, then I can hopefully divide out one of those factors with the x minus 3 on the bottom, right? The thing that's preventing me from evaluating this limit right now is that I can't plug in. If I try to plug in this 3, I'm going to get 0 on the bottom of my fraction, and I can't divide by 0. So I'm hoping to try to resolve that through factoring. And it turns out I can, because x squared plus 5x minus 24 does factor. I'm looking for two numbers that multiply together to give me negative 24 and add together to give me positive 5. And so those numbers that I'm looking for are x plus 8 and minus 3. So they do divide out. The x minus 3 and the x minus 3 divide out, and that's going to give me the limit as x goes to 3 of x plus 8. Now I no longer have that dividing by 0 problem, so I can go ahead and plug in. I get 3 plus 8, which works out to be 11. And that's the exact derivative here. That's not an approximation. I'm not going to say, oh, well, maybe it's 10.99 or something like that. No, I know that the derivative is exactly 11 because I evaluated the limit itself. So this video has showed you how to think about the value of the derivative for various different kinds of functions. So we've got numerical functions where we have a table of values, we've got graphical functions, and we've got these algebraic functions. And how we approach the problem is going to be different for each of those types of functions. But the idea is the same. The idea of taking 2 points that are as close together as we can make them and finding a slope, right? So that is a common idea through all the different types of functions.